Hi, this is Atakan Aral from University of Vienna. Today I would like to present you our paper, Reliability Management for Blockchain-Based Decentralized Multi-Cloud. This is a joint work with Rafael Burundoriarte from Kunsthistorisches Institut in Florence, Antoni Simone from iExec Blockchain Tech, and Ivona Brandic from Vienna University of Technology. Our paper was accepted for publication in CCGrid 2020. I would like to start my presentation with a definition of blockchain-based decentralized multi-cloud. In this architecture, service providers offer their services in the multi-cloud environment, and consumers search and contract with these services, resulting in more offerings and avoidance of vendor locking. All the transactions between providers and the consumers are registered in the blockchain. As a result, these two parties do not have to trust each other or any third party. The whole service lifecycle is automated, which includes the verification of the result correctness via consensus protocols. We need consensus protocols here because typically for reliability, each task is assigned to multiple workers, and at the end they have to reach an agreement with the results. We see the architecture here. Here the application and data providers create their application, services, or data and make them available in a digital marketplace, which is normally defined in a smart contract, and it also contains the offers for computing resources. Consumers negotiate with the services to access these applications and create a smart contract to manage the service provisioning. Then these tasks are scheduled or sent to the worker pools, which are a group of workers managed by a broker in charge, and they offer available computing resources, and they execute these tasks according to the terms defined in the smart contract. For example, this could be response time or reliability. The results are validated if correct, they are sent to the consumers. In this work, we focus on the validation and scheduling steps, and we aim to calculate the failure probability or probability of incorrect results and use this information in these two steps. There are certain challenges concerning reliability in this architecture. We would like to distinguish between two types of challenges. First is failure-free execution of the tasks. Since the providers contain small resources or even fog nodes, they could be prone to involuntary failures. The second type of challenge is the correctness of the result. While the first one is involuntary, the second one could be malicious activity, because the consumers have little or no knowledge of the resource location and ownership. So some of the providers might be malicious and they might try to return incomplete and incorrect results, but still get fully compensated. They could do this by joint ownership of the resources, and they might act maliciously only when they have the majority of the workers assigned to a single task. In the rest of this presentation, I will call this first type of failures as a failed task and the other one as an incorrect result. Our contributions in this work are three Bayesian network models for the reliability of providers, representing the correlation between these providers and also corresponding uncertainty. We also present a reliability predictor for the services that are executed by multiple providers based on these three models. And based on these reliability predictor, we also propose a task scheduling algorithm which exploits redundancy to give probabilistic guarantees for correctness. Finally, we extensively evaluate these algorithms and models using real traces from a blockchain-based decentralized multi-cloud platform, namely iExec, and also present our insights on the results. In this presentation, for brevity, I will focus only on the three models and a part of the experimental results. So, as I said, we propose three Bayesian networks. So let's start with what is a Bayesian network. It is a probabilistic graphical model that represents a set of variables and their conditional dependencies via a directed acyclic graph. In our case, the variables are workers, and their dependencies could be because of joint ownership, for example. And this example is an extract from our real trained Bayesian network coming from real data. Of course, it's a small part of it. And here we see, for example, worker 15 has dependencies to worker 7 and worker 13. And for each variable, we have a conditional probability table. And this is the table for worker 15. And we see that depending on the values of the variables worker 7 and worker 13, the probability of the value that worker 15 will take changes. So here in this small example, there are only two values, like 0 and 1, 0 representing no failure and 1 representing any type of failures. Of course, this is a huge simplification, and a big question is which values to use and how many values or states to use for realistic modeling of this architecture. As I said before, we propose three alternatives here, which result in three different Bayesian networks. The first one is the joint model, which jointly models both involuntary failures and malicious activity. So here, we see the different values the status of a worker can take. R is the worker status, I is the worker ID, and J is the task ID. In the first case, we have omega, which is the worker output, equal to the consensus result, which means the worker returns the same result as the consensus, so it is correctly executed. In the second case, the output is not equal to the consensus, but also it is not a null, which means the worker didn't return anything and it failed. So it means the worker does return a result, but it is different from the consensus, so it's an incorrect result, which might indicate some malicious activity. The next case is that the output of the worker is null, which means the worker has failed during the execution, so it couldn't provide any output. So this could mean an innocent failure, so to say. And the last case is that this worker, indicated with I, is not a set of the workers assigned to these tasks. As a result, its output is not relevant. So, in the blend model, instead, we combine these two cases where malicious or failed activities are represented into just one case. All the first case and the last case are the same. The middle case, on the other hand, says that the worker does not return the same result. So the output is not same as the consensus. It could be null or it could be an incorrect result. We are not interested if it is a malicious activity or just an innocent failure. Finally, in the dual model, we manage at the same time two Bayesian networks. One is focused only on the failures and one focused only on the malicious activity. Here, in the failure model, we have the first case saying that the worker returns a result. We don't care if it is a correct result or not, because we are only interested in the failures here. Next case, the worker fails and does not return a result, so the status is null. And the last case is the worker is not involved in this task. In the Bayesian network that is modeling the malicious activity, the first case is that the worker returns the same result as the consensus, which is the correct result. The second case, the worker returns a result, so it's not null, but it's not the same as the consensus. So it could be a malicious activity. And last case, we do not differentiate either it is not involved or it returns a null result. So it is the same when the worker doesn't return a result. So among these three models, joint model has the most detail because it separately models these two activities, and but blend, maybe this differentiation does not make sense. So to evaluate this, we also have the blend model, and dual model, on the other hand, has more detail for each individual type of challenge, but it misses the connection between these two. So this could be a problem as well. So we would like to evaluate how these models perform, also how our scheduler performs. For that, we used 3,000 tasks that run on the iExec platform in June 2019. And we used Monte Carlo simulation to address uncertainty in our models. We have other machine learning models as baselines. And since these kind of malicious activities are quite rare, we have to inject our failures into the datasets. I would like to give you two sets of results here. The first one is about the learning performance, and we measure it in terms of recall. And as we increase the number of malicious workers injected into the dataset, we could see that the learning performance increases because it's when there is more data, it is easier to learn from it. And as you can see, our proposed Bayesian network approach and the baseline random forests are the best performance in terms of learning. And if we zoom in that part and to compare that with corresponding confidence intervals, we can say that Bayesian network approach is slightly better. The second set of results that I would like to discuss is about comparing the three different models that we have in terms of how many tasks are still failed when we model the failures with these three models and schedule the tasks accordingly. And if we don't use any of the models and schedule them without considering reliability, as you can see, the number of failed tasks is much higher, and our proposed models can make a dramatic improvement in terms of failed tasks. And again, if we zoom into this part to compare between different models, we can say that joint and dual models are performing more or less the same, but one should also consider that dual model has a runtime performance issue because it has to manage two Bayesian networks at the same time, whereas the blend model, which is the simplest one, performs worse than the other two. There is a lot more in the paper to check. We explain our Bayesian reliability predictor there. We present our scheduling algorithm that we call reliability-aware task replication. This algorithm is based on graph partitioning, and we also present the complexity analysis of the algorithm. There are much more results as well in terms of accuracy, runtime performance, etc. Or we also have sensitivity analysis. And of course, we also described this threat injection mechanism for our experimental setup. So you can check the paper by scanning this QR code. So the key points from this work is, first, we have significant improvements in terms of number of failures. And we can do that by also using less amount of resources. So redundancy is less, but still the number of failures decrease significantly when we consider the reliability of the resources. We have two use cases for these models or algorithms. First, it could be they could be used in the definition of provider repetition, or they can be used for scheduling new services, as we did in this paper. There are obviously some limitations or directions for future work. First issue is that these malicious workers can simply create new profiles, and as a result, they can have a clean reputation. One solution for this is penalizing new profiles, but there is a delicate balance here because we also don't want to increase barriers to entry to the system for the new brokers or providers. Another thing is our approach is data dependent. So historical log traces have to be available for it to work. For now, the training phase is offline and the predictions are online. In the future, a possible direction could be also changing the training phase to an online learning mechanism, so that changes or new providers could be captured without retraining the model. Finally, another direction for improvement is incorporating other quality of service parameters, such as response time to the scheduler that we propose. Since the paper is already 1 year old, I would like to point out two of the more recent work from the authors. One is focused more on the failure prediction or failure modeling part of the problem, and the other one is more on the smart contracts part of the problem that you can check. So before ending my presentation, I would like to thank our funders, Austrian Science Fund and Marie Curie Actions, as well as Mr. Onatkaya for his valuable technical support. If you have questions or comments about the paper, you can contact me via this email or by scanning this QR code. And I would like to thank you for your attention.